Okay, sorry for the delay. I forgot to post the slides, so they are up there now. All right, so today we are going to cover prompt-based learning. So we're going to switch back to left to right language models and talk about how we can use these for solving downstream tasks. And then towards the end of this lecture, we will cover how you actually use language models, but train a very small number of new parameters to kind of adapt them to various different tasks. So, so far in this class, we've talked about basically two paradigms of pre-train and then fine-tune the whole model. Today, we're going to talk about some advances on the latter direction. How can you get the number of new parameters that you add or fine-tune down to a very, very small percentage, or even no new parameters added or fine-tuned to solve many different tasks. So first, let's take a step back and look at the history of these language model releases, these public checkpoints, and also OpenAI's API service, to get some perspective on how the size of these language models has been developing over the last 1 to 2 years. So this table was in the GPT-3 paper. You can see that they trained a bunch of different language models. They all had the same architecture. It's just a transformer language model trained to predict the next word. But you can see that they scaled up. They had a small version, which was 125 million parameters. So as a rough idea, this is a 12-layer decoder-only transformer. The dimensionality of these hidden states at every layer was 768. There are 12 attention heads in each layer. Each attention head's dimensionality was 64. This is a pretty enormous batch size of 500,000 token predictions per batch. But this is just the smallest thing. So in your projects, if you wanted to use a model like a language model, you would reasonably be expected to you would expect to be able to load a model like this into any GPU that you get on Colab and make some predictions. This one, though, if the last row here, the biggest GPT-3 model, the one that they primarily use for all of their experiments, is 175 billion parameters. So compared to this model, it's got 96 layers, way bigger model dimensionality, 96 heads per layer, way bigger batch size. So overall, like, this model is insanely huge, and it's not even the biggest one that is currently available. So this model is so large that OpenAI did not release the model because even if they did, it would be very hard for anyone to actually use it. So they released it as kind of an API where you have to pay to actually use the model, which calls into question, you know, how open really are they. But still, it's a nice service that now anyone can access and pay to use, this huge language model. And we'll see an example of using this model to solve a downstream task in later in this lecture. Okay. And just in comparison, right, we had Elmo, which was 93 million parameters, BERT large, 340 million parameters, and we've gone up to this, which is insane. And this is the same thing that's happened on the data side, right? So we went from about 1 billion training tokens back in 2018 to 300 billion tokens for GPT-3. So this is, you know, really, really large amount of data. It's hard to even fathom what kinds of things the model is learning from this kind of huge scale data. This is basically a curve showing the amount of compute used to train these models. This is on a log scale. And note that all of these models have come out in the last like 3-ish years. So there's been a huge advance in training both hardware and optimization and so on to allow for this. Late last year, there was an even bigger model released called Megatron Turing NLG, which is 530 billion parameters. There are probably many more models now that companies have internally that are even bigger than this. And so we'll talk later in this semester about what's called the scaling laws of language models, which shows that if everything else is equal and you have enough compute, one of the main results is that training a much, much bigger language model will allow you to generalize better from seeing fewer examples. So this is one reason why we're getting such huge language models trained. Okay, so on to the topic of today's lecture. What does this all buy us? Like, why are we training these bigger and bigger models that are literally just predicting the next word? That's all they're trained to do. Training one of these things costs millions and millions of dollars. So why are people doing this? And so if you looked at the GPT-3 paper, one of the reasons is that if you have a model that's sufficiently trained for this task of predicting the next word, you can actually use it with no further modification to solve many different tasks. So you can see that traditionally, if we wanted to solve a task like machine translation, we would show the model all of these pairs of parallel, like English to French sentences or phrases, and then the model would be updated to, every time it sees this training example in the future, do a better job at predicting this translation. And then finally, at test time, we would show it some phrase that it never saw before in its training data and see how well it translated that. So that's traditionally the fine-tuning process as we've all seen it in this class up till this point. So what these models kind of buy us is a very improved performance in a zero-shot setting. So if the model is given just a description of the task so you give a language model, in its prefix, you put a description of how you want to solve the task, the model should be able to solve it without seeing any actual labeled examples of the task. So you can imagine if this works, it's extremely powerful. You would not need to collect labeled data anymore. Instead, you could just tell your language model, I'm going to give you a sentence, predict the sentiment of the sentence, and it would do the whatever you intended. Of course, it's not that simple, as we'll see, but this is where all of this research is going, right? People want to get closer and closer to this ideal setting. So, for example, if you had just a giant language model, and into its prefix you put translate English to French, cheese, arrow, and you ask it to generate the next word, it would be really nice if it just generated the French translation of cheese, right? And conceivably it could do this without actually seeing any parallel data in its training process. Maybe it's seen in the 300 billion tokens that it's trained on, some examples of, learning French, and there are, examples formatted in this way that it can draw on to solve this kind of task. So there's no fine-tuning involved here. Basically, you just do pre-training on predicting the next word on a huge data set with a huge model, and then you just give it this prefix and ask it to predict the next word and see what happens. So this is a little difficult, right? Because maybe the model doesn't understand the format that you used in your prefix, right? What is this arrow? Maybe that's not optimal. Maybe it saw colons instead, or maybe there's a different format that would help the model output this translation. So you can also consider the one-shot setting, where in addition to giving it the description of the task you want to solve, you also give it one example. That seems, very easy to produce, right? So maybe you give it one example of an English phrase and its French translation in the format you want. Then you give it the one that you actually want to translate cheese and see what happens. Similarly, you could do the few-shot setting, where you just put some small number of examples into the prefix in the desired format, So, for example, translate English to French, sea otter, peppermint, plush giraffe. You put in their paper, they put up to 100 examples, or how many ever could fit in the prefix window, and then they give it the test held out word that they want to translate to French. Okay, so any questions on this? Yes.
How is it different from what
The question is, how is this different from what T5 is doing? So remember that T5 is pre-trained and then fine-tuned to solve a target task. So you have to show T5 labeled examples of whatever task you wanted to solve before it can actually do that task, right? Otherwise, remember, its pre-training task is to fill in these corrupted spans, right? So T5 is going to be a little confused if you give it something like this, right? It's not going to know what to produce. It needs to be taught how to solve this task. Other questions? So like the cool thing about this is that all you had to do was pre-train a language model, and provided you can come up with a good way to instruct it to perform some task, you'll be able to solve that task to some extent. So is the gradient being updated when giving the few examples? No. So in this case, the gradient, there are no gradients being computed. All you're doing is putting the instructions, concatenating them with a few examples, putting them into the language model, and then decoding from the language model using one of those decoding algorithms that we talked about, right? Either sampling or beam search or greedy decoding or something like that. There's no training at all in this whole process. Yeah.
More of a philosophy question, but on the spectrum of narrow AI to general AI, where do you think that this kind of thing called GPT-3 is on that spectrum?
So the question is, on the spectrum of narrow AI to general AI, where does this kind of thing fall on the spectrum? Well, as we'll see later on in this class, this, although seemingly remarkable, is very limited in the types of tasks it can solve. And sure, I mean, it's exciting if it can translate a few phrases or, you know, give you the sentiment of some review, but much more complicated tasks, you can imagine constructing some description of how to solve, and this thing will fail on those kinds of tasks. So there are definitely limitations to this approach, and when we do a little demo, you might be able to see some, I mean, depending on what happens, but yeah. Any other questions? Yes?
Why are we giving the example? Does it like to the model more like
So the question is, why are we giving these examples? So think about what's actually happening here. This stuff, right, the description and then all the examples in this format are being sent to the language model as a prefix, right? So then you're asking the model, given all of this stuff that you've seen in your prefix, so all of these examples of translations in this format, what is the most likely next word to predict? So you would expect that if the model sees examples of, you know, French phrases and, you know, this arrow, you have an English arrow, French, maybe it will pick up on that pattern and realize that, okay, I saw an arrow, maybe I should produce a French thing now. Okay, it seems like all the other things in my prefix are actually translations of the phrase that precedes this arrow, so maybe I should produce a translation. I mean, that's kind of the intuition. It's hard to know what the model is actually doing, but it does show some impressive generalizability for, you know, like even addition or basic arithmetic it can do, where you might not expect that it has seen all of these examples before in its training data and it's just retrieving them. I mean, this one you might expect, like in 300 billion words, maybe there are many instances of cheese followed by the French translation, right? In any sort of learning French website, you might get this over and over again. But other things are more impressive, I think. Okay, so, okay, let's do an example. So I wanted to go to this OpenAI GPT-3 thing, and this afternoon I made a prompt to solve sentiment analysis. So Here was my prompt. So I basically just took a bunch of sentences from movie reviews and constructed a prompt. You'll notice that here I don't have any task instructions at all. So you don't really need those if you're going to just give examples of the task and it's pretty obvious, then I decided not to bother. We can try including some though. So you can see the format here is, here's a sentence from a review, and there's this arrow and then the label, positive or negative, right? So this one is positive, this one is negative, this is positive, this is negative. You know, I just shoved a bunch of examples into here. So what happens if I click generate is that this whole prefix is sent to GPT-3, and it will use sampling to sample some next words for me. And so at the end, I have let's say this last sentence here. With its stilted dialogue and hammy acting, the film has the look of an expensive production, but the feel of a B movie delivering the sort of undemanding monster mayhem Arnie's fans have come to expect. So this is clearly a negative sentiment sentence. So I'll put this arrow here, and now I'll ask the model to generate. So it gets all of this as its prefix, and I'm asking it predict the next word. And hopefully it will be negative. Let's see. Negative. Okay, so that's good. Does anyone want to give me a sentence, if you can come up with one, and want to see if this model can predict it? Maybe a positive sentence? No one? Okay, maybe I'll find one then. All right, name a movie. Someone name a movie. The new one? The Batman? The Batman reviews. Okay. All right, how about this one? Pattinson does a great job. Oops, did I copy it? Oh my God, I can't copy this. Okay, here we go. All right, so I put in this, Pattinson. I mean, this is pretty straightforward, right? This should be positive. It says phenomenal, although that inner torment might be a little negative. Let's see what happens here. Okay, so it did good. One thing I wanted to note is that this kind of prompt-based, so this essentially is an instance of a discrete prompt. We'll see this terminology more in this lecture, where you are just providing words to the model to instruct it on how to solve a task. In this case, we're just giving it examples of the sentiment task. Let's see, one thing that I was trying to figure out is if I remove this example from the prompt, a nice girl like you, a stilted, outdated, unbelievably based on a true story rom-com. So this negative sentence, note that it contains the word stilted. And then I tried to predict this sentence. It was actually positive. So this is the first thing I tried. And I was wondering, why does it think that this is positive? And one hypothesis I had was maybe it doesn't know what stilted means. I mean, it's kind of hard to tell what this huge language model knows. So then I added this to, the prefix, this sentence that contains the word stilted and is paired with negative. And if you do that, it predicts negative. So now you can actually start to kind of probe the model, right? What if I take this word stilted and replace it with some other word like boring or something? Will it still work? No. So you can see how brittle this kind of approach is, right? Like its performance on the sentiment task really depends on the quality of the prompt and how expressive the prompt is. Yeah.
You think if it's kind of unsure, it might have like a 50-50 probability on the token color, right? Like I know it's in one, not sure. Do you think turning down the temperature would force it to select the one that it thinks?
Yeah, so the question is, because we're sampling from this model, perhaps the model is unsure here and it has like 50-50 on positive or negative, and sampling we get one thing that is just a sample from this distribution. If we do it a couple times, maybe we can see the uncertainty, or maybe we can turn down the temperature. So we haven't talked about temperature, but it's a hyperparameter in the softmax function that controls like the peakiness of the distribution. So you can see here, they give you an explanation for temperature. Lowering the temperature results in less randomness. As the temperature approaches 0, the model will become deterministic and repetitive. So basically, it'll always choose the most probable thing. So sure, let's turn it down to 0 and see what happens here. And maybe I'll get rid of, oh no, we can use this one. So it's still positive, still positive. So clearly the model is kind of brittle, right? Yeah. Yeah, so that's also a good question. Does the sequence of examples, the ordering of these examples, could it change the results? So it certainly could. That's another potential issue with this kind of approach and we'll see some examples later on of even more things that break this kind of approach. But all in all, it's impressive that the model can learn to predict positive or negative and roughly get the sentiment right in most cases, but it's also not always perfect. It's not at all perfect, in fact, and it has a high dependence on what you put into the prefix, how you format the prompt. So that's what I wanted to show. Could this produce translations in a language similar to the target language, but not the language we want? Yes. So this is actually a big problem with if you're trying to do both translation or any sort of multilingual or cross-lingual task. So say you give the model an English document and you tell it, give me a summary of this document in French. Now the model oftentimes will produce a summary but in English, or it'll produce some French text but it's not a summary. It's very hard to control in these cross-lingual things. These kinds of tasks are usually solved with multilingual language models, which we'll talk about next week. But yeah, we'll see more instances of this in the lecture on multilingual language models. All right, so that was our example. Okay, so now let's look at some experimental results. We already saw that this zero-shot or few-shot prompt-based approach, where there's no model training at all, can be kind of impressive, but also not super great. They evaluate in the GPT-3 paper their model on many different tasks in the zero-shot, few-shot settings and compare it to full model fine-tuning. So on this task of trivia QA, this is a question answering task where the model is given a question like, who was Poop Deck Pappy's most famous son? And you're supposed to just produce the entity that answers this question. So I think most of the questions here, their answers are entities, so like people, places, or things, or numbers like dates or something like that. And so you can see that first of all, this dashed line at the top was the previous state of the art on trivia QA. This was probably some sort of BERT or Roberta-based model that was pre-trained and then fine-tuned on the trivia QA training set to solve this task. And an interesting plot in their paper shows the accuracy of the zero-shot, one-shot, and few-shot models. So here the few-shot GPT-3 gets 64 trivia QA questions and answers in the prefix, and then gets a test question and is asked to generate the answer to the question, right? So look at the tiny model, the 0.1, the 100 million parameter model, GPT-3 small. You see that none of these approaches is very good, right? You get an accuracy of under 10%. The fine-tuning accuracy is close to 70%. There's a huge gap. But you can see the power of scaling up this approach, right? So as you get to a 175 billion parameter model, the few-shot approach with 64 QA pairs in the prefix actually surpasses the previous state of the art, which was using the entire Trivia QA training data to fine-tune the model. So this is quite a remarkable result, right? The giant pre-trained language model with no gradient updates to specialize it for this task is doing better than a completely specialized question answering model on this data set. So maybe we can now think about how could this result happen? Like what does this mean? What does this say about the capabilities of GPT-3 at this scale? Does anyone have any ideas?
Well, it seems like it's able to use the huge number of parameters to encode, store a lot of information about the real world, so that when it asks questions about the world, it has like almost past knowledge to apply.
Yeah, exactly. So this data set, all of the answers and the questions are about relatively well-known or famous entities because they're all trivia questions. So at some level, people have to know about the concept in order to answer the question, right? And so GPT-3, in its 300 billion tokens of training data, we'll see many, many examples of all of these entities being used in different scenarios with different relations, attaching them to other entities and so on. And what this curve essentially shows is that as you increase the number of parameters in this transformer language model, it's able to memorize more and more of that information from its pre-training data about different entities and their relations to each other. And this memorization ability is enabling it to perform very well on this Trivia QA task. Essentially, it knows a lot more about the world than a model that has been specialized to Trivia QA's training data set, right? This model, GPT-3, could have seen a lot of instances of entities that are asked about in the test set in its giant pre-training data. So, essentially one takeaway is that as you scale up a language model, it becomes better and better at being able to memorize facts from the training data. Now, it would be interesting if you took a data set similar to Trivia QA, but replaced all of the entities with like synthetic ones that you would never expect to observe in the real world, and then see what happens to the performance of all of these models. So I think people are doing experiments like this, trying to analyze if it can actually develop some sort of reasoning abilities as opposed to just memorizing things. And so far the results are, I think, a little mixed. Okay, so let's look at translation. Translation is the example we started with here, translating like cheese into French. Note that 7% of GPT-3's training data is in languages other than English. So they trained it on this dump of like the common crawl that was kind of cleaned, but it's hard to actually clean it fully. There's a lot of non-English data. Even 7%, although it seems small, remember we have 300 billion tokens, so it's actually quite a lot of non-English data. And they compare, again, their zero-shot, few-shot, and one-shot approaches to state-of-the-art supervised translation systems that actually get parallel, in some cases millions of parallel sentence pairs in language X and language Y to train their system. So you can see that if we compare the few-shot GPT-3 approach to the state-of-the-art, this is the blue score, which we haven't actually talked about in this class, in this semester yet, but we will either next time or next week. Basically, it's a measure of how good of a translation did the model output. And a gap of 13 blue is very significant. That means that GPT-3 is much worse than a supervised machine translation system on translating from English to French. But you can see on some other language pairs, it's a little more mixed, right? So, for example, French to English, this state-of-the-art model was 35 blue, and GPT-3 was getting 39. English to Romanian is pretty bad for GPT-3. Translating into English always seems better. This kind of makes sense because GPT-3 has a huge amount of English data. So it just needs to roughly learn that it needs to do the translation into English and have some vague idea about the meaning, even if it gets it a little bit wrong. The supervised translation systems aren't that great for under-resourced languages either. So yeah, I mean, all in all, not so great at translation compared to supervised models, but it's still much better than like outputting random gibberish, right? This is doing something. Okay, we have a question. If a language, for example, Arabic, was not written using Latin letters, does it still capture it as Arabic and not English? I'm not actually sure what they did in this paper. Maybe they removed such text, but in the other models that we'll discuss next week, the multilingual models, they preserve all of these languages even if they are not using the script. So yeah, I'm not sure. It's probably written in the GPT-3 paper somewhere, but I can't remember. Okay, so another thing that they show is that the improvements have not plateaued on translation, so this could be promising for anyone who wants to train even bigger language models on even more data. Probably that includes more multilingual data. Perhaps you will get a better translation model without any supervision. Okay, finally, they look at reading comprehension question answering. So we looked at this in Squad, for example, where we have a document, we have a question, the answer is a span of text within that document. So on all of these data sets, we see that the fine-tuned state-of-the-art model, which has access to the full training data of this task, these models are always better. But we see that for some data sets, GPT-3 is quite close. And for other ones that are supposed to be harder, they're designed to be harder in some way. Either the questions are hard or they're in different settings. Like, for example, this is in a conversational setting where you need to model the history of a conversation. GPT-3 is much worse than a fine-tuned model. So this suggests that there are many tasks for which the simple approach of just putting in a task description and a couple examples from the training data into the prefix and doing no training at all and just generating a next word, this is a limited approach. So all in all, it's kind of promising, but it's limited and does not work for all tasks. All right, so this is a more recent figure showing some of the performances of the big language models compared to their number of parameters. On this side is the GLUE score. So remember that GLUE is a benchmark of NLP classification tasks. It's like 9 or 10 tasks, and their scores are all averaged together. People have been developing on this, developing their language models, using it as a kind of proxy for general language understanding, even though it's extremely limited, and now people are using other benchmarks that have more variety than just classification tasks. But basically, the GLUE scores have been going up as we increase the number of parameters. So to motivate the next part of this lecture, we should think about some of the practical challenges of having these huge scale models. So they definitely do give you good performance, especially when they're fine-tuned on the downstream task, instead of, as we just saw, just being instructed to solve a task. But it's very costly to share them, first of all. Like if I shared GPT-3 with you, first of all, I don't know how I would do that. Second of all, there's no way you could even load it into GPU memory, let alone do a forward pass without some extensive engineering, it wouldn't be possible. Even for companies, it's hard to serve predictions from these models. So imagine you have, you have a base language model like GPT-3, and you've fine-tuned it to perform 100 different tasks. And now you offer each of those tasks as an API to customers. So if they wanted a sentiment model, they could issue queries to your sentiment fine-tuned GPT-3. If they wanted a QA model, they could use a different thing, and so on. So now you have 100 copies of this model, and you want to serve its predictions, and it becomes very challenging. You have many different input queries coming in. They're all using the same base model, but if you've done fine-tuning, you can't reuse one model for another task. So the approach we saw over here, this approach, there's no issue with having to serve or share multiple models, right? It's all one model, and the only thing that's changing is a prefix. So it becomes much easier to serve these kinds of queries, because if you wanted a sentiment prediction, you could just put in, give me the sentiment of the sentence, and so on. And it's using the exact same model as if you wanted a question answering output. You would just, in the prefix, say, give me the answer to this question, blah, 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 right? So that makes both sharing and serving much easier. But we know that this approach is now limited, right? It does not really compare to the fine-tuned state-of-the-art on more complicated tasks. So can we kind of merge the two approaches is the next step that we're going to talk about here. So basically, we would like to get the advantages of having a single base model, but we would also like to get some of the advantages of fine-tuning, where our performance is going up as the model gets specialized on a downstream task. So that motivates this approach of prompt tuning, which is in this paper, Lester et al. 2021 at NLP, and was one of your readings. So we want to kind of get from this paradigm of we have a prompt that's completely in text and is manually designed, right, by a human. We have to decide whether we want to say translate English to German : or whether we want to drop this colon, or whether we want to format this some other way. And with no gradient updates or fine-tuning, what happens if we allow the model to learn a very small number of parameters instead of fine-tuning the whole model? So now it's kind of a middle ground between the zero-shot approach and the full model fine-tuning approach. And maybe this will make our challenges of sharing and serving these models go away while still retaining the performance of the full fine-tuned model. Okay, so in this paper, they identified several issues with the discrete prompts, like we just saw on the GPT-3 side. So the discrete prompts are natural language. The problems, they require some understanding of the model's inner workings. We saw that when we were trying to debug why is the model failing on this example that includes the word stilted. Is it that it doesn't understand this word? Maybe if I give it an example of this word in its prefix, then it'll be able to solve it. But you can imagine iterating over this prompt is quite a painful process. We also saw that the performance is much worse than they use the term model tuning, which refers to fine-tuning the entire model on a downstream task. It just basically the fine-tuning that we've seen in this class so far. Okay, so here's a great example to illustrate the issue. In this task, you're trying to, basically you give it one of X or Y, and you're trying to have a model predict the missing entity. So like X is located in Y. So for example, you could say Amherst is located in blank, and maybe the answer is like, or Amherst is located in the state of blank, and you might want it to produce Massachusetts, right? But there are many ways in which you can ask this kind of question, right? You can say, is located in which state, or is located in which country or state? Question mark, so you can ask it as a question and then have the answer followed by a period. You can just turn it into a statement instead. X is located in Y. You can say X is located in which country, question mark, in Y. You can imagine so many permutations of all of these prompts. And annoyingly, the performance, so here they're showing the precision at 1, is highly dependent on the format of the prompt. So asking X is located in which country, question mark, in why. This format of the prompt, it gives you 51%, but the same exact thing without the in drops you by 20 points. So you can see how brittle this kind of prompt, discrete prompt engineering is. Okay, so what we want to do is shift away from the discrete prompts to continuous prompts. And this is the idea behind prompt tuning. So if you look down here, we're talking about additional learnable parameters that are injected into the model while keeping most of the model frozen. So if we have, for example, 99% of our model is not touched during the fine-tuning process, and maybe 1% of the model is some new parameters that we introduced to solve this task, can we still close this gap to full model tuning? Okay, and there are many strategies on how to learn these continuous prompts. We have prefix tuning, soft prompts, and what we're going to talk about today is prompt tuning. So I'm going to go onto the iPad to explain this fully, but intuitively at a high level, you can imagine your prefix to a language model consisting of word embeddings for whatever the words in the prefix are. And what happens in prompt tuning is that we're going to learn a new sequence of embeddings that is prepended to the input of the language model. And these embeddings are going to be the same for every instance of the task that we want to solve. So instead of telling the model, I'm instructing you to give me the sentiment of this sentence, we'll instead learn a sequence of word embeddings that the model interprets much more effectively to perform the sentiment task. So with that, that probably wasn't super clear, but maybe it'll be more clear when I switch to the iPad. So let me do that. All right. So I think just to make things clear with regards to model tuning versus whatever we've been talking about in this lecture, first let's take the T5 model that we saw in the last week, and let's go over the process we use to specialize this model for a downstream task. So let's say sentiment analysis. All right, so we're going to be explaining today the prompt tuning algorithm of Lester et al. And this approach just came out late last year, so it's very new, but a lot of people have been developing on top of this method, including some of the work in my lab, which I'll talk about a little bit later. But let's start with this T5 model. So this approach was developed by Google. Google also developed the T5 model, so of course they're going to show that it works through experiments on the T5 model. So remember in T5 we have this encoder-decoder transformer, right? So we get this movie is awesome. We have our embeddings. These are fed into a encoder, right? So here we have unmasked transformer encoder, and then we get some vectors as output. And now we have a decoder, right? So the decoder gets like this start of sequence token, passing it to a transformer decoder. So remember the decoder is doing masked self-attention on its decoder side inputs, and it's also doing cross-attention on top of the encoder's inputs, right? And so now, given the start of sequence token, the decoder produces something, and from this, we're going to ask the model to predict the word positive using the softmax layer. And remember, the softmax layer includes the entire vocabulary as potential outputs. So the model is generating the word positive, right? That was our goal. So in T5, in the approach that we talked about pre-training this model using the corrupting, like removing spans from the input and then asking the decoder to predict the missing spans of text, right? That was a pre-training process. And then we talked about fine-tuning the model. So given the pre-trained model, we put in labeled sentiment examples. So like, this movie is awesome, should be positive. And we fine-tune the model to, given this example, you pass it through the encoder, and then you pass it through the decoder, and then you do backprop once you get this final prediction, so that the next time the model sees this example, it will have a higher probability of predicting positive, right? So when we're doing backprop, we start at the softmax layer, we backprop all into the decoder, we backprop into the encoder through the cross attention, and we backprop all the way down into the word embeddings, right? So what is getting changed here? What parameters are getting updated here? Every single part of the model is getting updated through this fine-tuning process, right? All of the transformer blocks in the decoder and the encoder, all of those query key value matrices and the feed-forward weight matrices, all of those things are being more specialized to the sentiment task. So in this approach, fine-tuning, whole model. This is called model tuning in their terminology, so we'll stick with that for the rest of this lecture. All params of the model are updated during backprop. And so this is the state-of-the-art approach for most tasks, right? You update every single one of the pre-trained model's parameters to specialize it to some downstream task. Now the problem with this is that every time I want to have a new model for a new downstream task, I have to create a copy of the pre-trained model and then fine-tune it for that task, and it can no longer be used to solve any other task, right? This model, once I do this fine-tuning, it can only do sentiment, and it can't ever solve any other task unless you do more fine-tuning on it. So it's not really great for shareability, right? Because now I have to have hundreds of copies of my model if I wanted to share copies of the model that perform 100 different tasks. And it's not good for people serving these models, because every time someone wants to get a sentiment prediction, I have to go load the sentiment model and then give the prediction, so this can quickly get expensive with a lot of different tasks. Not to mention the problems with batching. So one thing we would like to do is retain the performance of this full model tuning approach while not actually updating all of these parameters. That would be great, because then you can imagine for a new task, we just say, all right, replace these parameters with replace the small number of parameters in the base model with some other values, and you're now good to go for solving sentiment analysis or something like this. So prompt tuning works as follows. So now let's say we have the same sentence, this movie is awesome. And we have our word embeddings. So the main change here is that instead of just feeding these embeddings into our encoder, we're now going to add prepend some new learned embeddings to the model. Let's say I add 2 new embeddings to this model. These embeddings are randomly initialized. They are not part of the vocabulary, they're just basically at the start of this process, they're just like random vectors that have been prepended to this sequence. So you cannot associate any of these with a word in the vocabulary. They are not words. This is the point of the continuous prompt, is that it allows the model to best learn these embeddings to facilitate solving the downstream task. It takes away, so if I were doing discrete prompts, I might associate these embeddings with something like sentiment analysis. And we know that there are many ways to format this. I could say, give me the sentiment of this sentence, colon. I could say, what is the sentiment of this sentence, question mark. I could just say sentiment analysis. This is probably a pretty bad one. But our goal is to remove this element of manual prompt design from the part of the user and shift that over to the model. So now we're gonna, instead of having this, we're just going to randomly initialize some vectors that are of the same size of our word embeddings. And so let's say randomly initialize. And now we're going to feed this whole sequence into our transformer encoder. So our encoder is now getting the 4 embeddings associated with the words in the sentence. It's also getting these 2 new embeddings that do not correspond to words, and initially it won't have any idea what to do with these. And so now it's going to produce all of these vectors. So it'll produce the 4 vectors for these, and then it'll produce some contextualized vectors for the new embeddings that we've added into this sequence. Then our decoder proceeds as usual. We have the start of sequence token. It gets passed to the decoder. And we have a vector which we're predicting positive from. And our decoder is attached to our encoder via cross attention. So now, when we're doing backprop, we're going to do something a little different. So remember that in normal fine-tuning, I'm going to update all of the parameters of my model. In prompt tuning, when I compute my loss at the softmax layer of the decoder, so here when I'm predicting positive, I'm going to compute the gradient, but this dotted line means I'm not actually going to perform any updates to the parameters. So I compute the partial derivative of the loss with respect to the softmax matrix, then I do backprop into the decoder, then I do backprop through the cross attention, then I do backprop through the all of the transformer blocks in the encoder, and finally I do backprop into the encoder, and then the only thing that I actually change in this whole process is these 2 embeddings here. So I'm only going to apply my gradient updates to the 2 new embeddings that I've prepended to this sequence. So let's make a little legend here to make that clear. So the solid line means that we're going to perform updates, and the dashed line means we're going to not perform updates. So, whoa. Sorry. Perform updates, and here we're going to no updates, frozen. So if you think about what is happening here, 99.9% of the model is not getting any updates through this process. The only thing that is changing are these two embeddings that we prepended to the input. So what might happen in this case? You might expect that these two embeddings, if the loss is actually going down, which means the model is getting better at predicting positive and negative or whatever, depending on the sentiment example, that means that the model is actually learning some vectors that it's prepended that are acting as an effective prompt for the task of sentiment analysis. So we aren't telling the model, explicitly perform sentiment on the following sentence. The model is learning perhaps the optimal continuous representation of that instruction. And as a result, this approach is generally much better than having discrete prompts that you design yourself. So I'm going to pause here. Are there any questions? I covered quite a bit.
If there are 5 tasks that we are trying to perform on this model, we can have one copy of the parameters that are being shared across all of the tasks, and each of the tasks will actually be having their particular copy of the embeddings for the prompt.
Yeah, exactly. So the question is, let's say I have 5 different tasks and I want to apply prompt tuning to solve all 5 tasks. I have one shared T5 model, the pre-trained model, which is going to be used to solve all of the tasks. And to solve each task, all I have are these embeddings, these 2 learned prompt embeddings, which I can swap out depending on the task, right? So maybe these 2 are learned for sentiment analysis, and I learned 2 other ones for question answering. And if I wanted to switch between question answering and sentiment, all I had to do was change the prefix of the model to include those learned embeddings. So you can see that in terms of sharing and serving this kind of model, you just have to store one model and these couple task-specific parameters for them. Yeah. Other questions?
Do you know if anyone has tried to take those learned embeddings and do like a mirror search in the vocabulary?
Yeah, that's a great question. So the question is, after doing prompt tuning, you get these 2 embeddings, right? Can you then do a nearest neighbor search in your vocabulary to all the word embeddings to see, maybe this embedding is close to sentiment and this to analysis? They actually do in the prompt tuning paper do something like this, I think maybe in the appendix or something like that. And they find that there's no real order to the learned. So the sequences in their paper are up to 100 learned vectors, so not 2 as I've shown here. And many of them are the same, like their nearest neighbors are the same. Sometimes they correspond to the class labels, so like positive or negative could be in here. Sometimes that corresponds to, I don't know, like words that are indicative of sentiment, like good or bad. They have some concrete examples in their paper. And later on, we found that if you initialize these embeddings not randomly, but you can get improved performance by, say, initializing them to the class label embedding average, or initializing them with a discrete prompt, like, what is the sentiment of the sentence, and then let the model fine-tune into it. All of these do better. So that also leads to the point that these embeddings are outside of the space of all of the word embeddings, right? There's nothing it's telling the model that the nearest neighbors here should be meaningful in any way. So it's hard to actually do this interpretation. But yeah, the nearest neighbors do seem to correspond to the task. So at least there's some correlation there. Yes?
What I see, we are actually just trying to make it more clear that this is a task. This is a task we'll be working on 4 years. So finding based on everything is wrong. So does this have any effect on the performance of these models on that particular aspect? Like why should it be wrong? Would that have any improvement?
Yeah, so the question is about performance improvements. So maybe we'll switch back to the slides and talk about that. So this approach is very attractive in many ways because you only have to store these embeddings to solve a task, and you can use the same base model. But it also does incur a performance penalty compared to full model tuning. Okay, so how do I do this? Oh. So the prompt tokens are the blue blocks, yes. And the desired response is this movie is awesome. No, sorry. So the input is the blue blocks concatenated with this movie is awesome. So maybe I'll make that clear, that this whole thing is the input. And the output of the model is positive. So we want the model to generate the label corresponding to this input for the task of sentiment analysis. All right, so let's go back to the slides. So now we've covered prompt tuning. And one advantage of this kind of prompt tuning is that in the same batch, so remember that we're usually working with batches. In the same batch, we can solve many different tasks because for each different task, we just have to prepend a different set of word embeddings, and the same base model is used. So you can have these mixed task batches where you have your real inputs and then you prepend different task prompts to solve, like A could be sentiment, B could be QA, C could be summarization. All of those are using the same underlying model with just some embeddings changes, so you can efficiently serve this kind of thing. Okay, so back to your question, what is the performance of this? You see the orange curve here, and this is on a benchmark called superglue, which consists of more complex tasks than glue. You see the orange curve is corresponding to model tuning, so where all of the parameters of the model are adjusted to specialize to the target task. And then you see here the square blue curve. This one is associated with manual prompt design. So if you had a discrete prompt that you yourself made, this would be your performance. And finally, the green curve in the middle is associated with prompt tuning. And the curve basically shows that as your base model becomes bigger and bigger, so similar to what we've seen, as you use a bigger and bigger language model, it's actually able to become much more competitive with full model tuning. But at smaller model sizes, the gap can be quite large. So this, again, is suggesting that as you get bigger and bigger language models, they start to have different capabilities than smaller ones, right? Maybe they're able to memorize more, they're able to generalize to different types of reasoning that is required. Whatever the case may be, empirically at least, if you have a big enough base model, you don't need to add as many new parameters or change many of the pre-trained parameters to solve a bunch of tasks. So that's in response to your question. Okay, and this curve also suggests some nice avenues for improving this kind of method. So, there are gaps in performance at smaller model sizes that of course, people are interested in closing. And also, the performance of prompt tuning is not very stable at the smaller model sizes. So you could learn 2 sets of embeddings for the same task that are completely different with different random seeds, and their performance could be very different from each other. So those are 2 things that are important. So here, there are different types of these kinds of prompt tuning based approaches. So the thing I showed you has just one sequence of embeddings prepended to the input. Prefix tuning is a method that adds these new embedding parameters to every layer of the network, not just the input. So you're adding more parameters. You can see here the task parameters. So this is the number of new parameters that are getting fine-tuned by the target downstream task. Prompt tuning at the biggest model size is giving you like adding 0.001% new task-specific parameters to the model, and the rest are all preserved from pre-training. Versus you see with model tuning, of course, you're at 100% of the parameters are being fine-tuned. So It's important in all of these cases to try and minimize the number of task-specific parameters. That just makes your model more flexible and your base model is more capable of solving all these tasks. So another question in this kind of setup is, how many new embeddings do you learn? So on our iPad, we showed adding 2. In their paper, they try from 1 to 150. So you can add 150 embeddings into the prefix and make the model learn those. And you see that they're kind of diminishing returns. So 1 is not great so just 1 embedding associated with the task is not great with the smaller models, but at the largest model size, it's not actually that bad. And 150, so adding more of these embeddings is not necessarily better. The best result seems to be with 100 of these, but it's hard to say. It seems to vary across depending on the model size and so on. So this is pretty interesting. You can't just get better and better results by adding more and more parameters into the task embeddings in the input. And going to your question, you can do better by cleverly initializing your embeddings instead of randomly initializing them. Although at the biggest size, again, it doesn't seem to matter. So biggest takeaway is that at the biggest scale of these language models, even a very, very simple approach with few added parameters can get you great performance. Okay, and I wanted to conclude with some work that my student Tu Vu has done. Actually, many of these slides are made by him. He's working on this stuff. One thing that you can do is kind of port over the pre-training and fine-tuning paradigm to strictly prompts and not models. So in the iPad, I showed you that we randomly initialize these prompt embeddings, and then we fine-tune them using the sentiment signal. But you can also initialize your prompt embeddings randomly, and then pre-train those embeddings on a different task. So maybe you pre-train them on language modeling, or you pre-train them on textual entailment, or some other task, and then you fine-tune that prompt on a task like sentiment analysis. So this work is called SPOT. It's like soft prompt, I forget what it stands for. Oh, soft prompt transfer. But basically it means that you can kind of close that gap that we saw between the model tuning and the prompt tuning at the smaller model sizes by pre-training your prompts using different NLP tasks. So you can actually do it on multiple different tasks, and you get a prompt that even if the pre-training task is unrelated to your downstream task, it actually acts as a kind of, it teaches the model that this part of the input sequence is kind of an instruction, and the part following this is an actual input. So you get pretty nice gains by doing this prompt pre-training. But there's a lot of ongoing research now in this area, even though these kinds of methods only became popular towards the end of last year, and now it's kind of a mainstream research direction within NLP. I think it's a good one too, because basically all these big industry labs are the only people who are able to train the huge scale models. It would be good if for any new task you didn't have to retrain or even train at all any of these big models, but you could just do some minimal modification to the input and get it to give you state-of-the-art results on some downstream task that you care about. So it's kind of one model is solving all of these tasks is the goal. All right, so I think that's all I had. Any questions? Yes. Yeah, so there are two questions, I guess. The first question is, in prompt tuning, in the sentiment analysis example, maybe I can go back to that, we add these two new embeddings, right, these ones here, first, are they tied to any words in the vocabulary? No, they're not. So in the way I described it, we randomly initialize them with arbitrary numbers. They're not corresponding to any words in our vocabulary, and they're updated through this fine-tuning process. So the other question you asked, if I have a task like emotion analysis, which is close to sentiment analysis, can I use these same two embeddings, or do I have to learn a new set of embeddings for this task? It kind of depends on your output space. So if it's still positive and negative in emotion analysis, then you could probably get away with using the same embeddings, although I think the spot approach on that last slide is probably the best course of action. So you pre-train your embeddings on sentiment and then fine-tune them on the emotion analysis data set. But let's say your emotion analysis task has like 5 labels, like sad, happy, or angry, or whatever. Then you certainly cannot use the embeddings for the sentiment task, because it's basically teaching the model you always have to output positive or negative, and those may not even be labels in your emotion analysis task. So it kind of depends on the task. Other questions? All right, so see you all on Wednesday.